Our presenter is Steve Milan from the University of Leicester. So Steve studied physics with astrophysics at the University of Leicester, graduating in 1990 before undertaking a PhD in the ionospheric physics group, which later became the radio and space plasma physics group, and that's now the Planetary Science Group. Steve became a lecturer at Leicester in 2001, reader in 2007, and professor in 2011. Steve was a visiting research fellow at the National Institute for Polar Research in Tokyo in 2000, and between 2013 and 2023, he was a visiting adjunct professor at the Birkeland Centre for Space Sciences, University of Bergen in Norway. From 2013, Steve was the PI for ground-based support of the ESA's cluster mission, for which he was awarded an ESA award for outstanding contribution to the cluster mission in 2005. Steve was awarded the European Geophysical Society's Young Scientists Publication Award in 2001 and the Royal Astronomical Society's Chapman Medal in 2013. Steve has been an associate editor of the Geophysical Research Letters and the Journal of Geophysical Research. He was a topical editor for Annuals of Physicae, and Steve was lead proposer for the Ravens and Janus mission concept to the ESA's M3, M4, and M5 cores, and the leader of the ESA science definition team for the Kyofu B from 2011 to 2012. So today, Steve's seminar is titled The Occurrence and Causes of Geomagnetic Disturbances that Produce Large dB by dt. So I'll hand over to you now, Steve, to present your seminar.
Yeah, thanks very much, Rosie. I'd like to say thank you to the MIST organisers for inviting me to give this seminar. I'd also like to apologise in advance because there's roadworks outside my house and quite a lot of traffic, and there'll probably be quite a bit of outside noise. That was the number 44 bus that went by just before, so I do apologise. Anyway, what I'd like to do today is talk a little bit about some of the work that we've been doing on dB by dt. This is myself, and I'd also like to highlight some of the work done by Gemma Bauer, Amy Fleetham, and Rosie Hodnett as well, who are working on this topic as well as other ones. And I've also got Audrey Shillings here, who visited us for a year a few months ago, and she's been doing this sort of work as well. So what am I going to talk about? So sudden changes in ionospheric currents induce currents in the ground, which then try to flow through conductors such as power grids and oil pipelines, and can be hazardous for that technology. We call the currents that are induced in these geomagnetically induced currents, or GICs, and they've been quite of some interest in recent years. I'd like to highlight that at Leicester we're not doing this in isolation, but what I'm going to talk about is very complementary to work that's being done at Lancaster and Northumbria, DIAS and BGS as well. And I apologise if there's anyone else that I've forgotten. So it is quite an active topic just at the moment. So what do we know about dB by dt? There are two main hotspots of dB by dt which occur. There's one in the pre-midnight sector and one in the dawn sector, which I'm highlighting in this figure here. And we measure these GICs with, or not GICs, rather, I'm going to be talking about the magnetic deflections that can cause GICs, because they're much easier to measure. And we measure these in both the north-south and the east-west component of magnetic measurements on the ground. And a second thing that this study here is highlighting is that these deflections tend to be north-south orientated in the pre-midnight sector and east-west directed in the dawn sector. So what we're interested in doing is working out how big these things can be, how often they occur, and under what conditions they occur as well. So that's going to be the topic of this talk. So how do we get these magnetic deflections on the ground? Well, they're produced by currents that are flowing in the ionosphere overhead. and those currents don't come out of nowhere. They have to be fed from somewhere else, and they're fed from the magnetosphere above. So currents flow in and out of the ionosphere in two rings known as the region 1 and region 2 currents, and then these are closed by currents flowing between those. So in this diagram here, I'm kind of indicating upwards and downwards currents shown by the circles with crosses and the circles with dots here, and then green arrows which are closing those. These are known as Peterson currents. And associated with those as well, there's the orange currents that I'm showing, which are Hall currents. And in general, if you're interested in magnetic deflections on the ground produced by these currents, it's actually the Hall currents that we're most interested in, because they produce significant magnetic deflections, whereas the Peterson currents tend not to, because they cancel out with the magnetic perturbations produced by the field line currents. So it's really these orange currents in general that are going to be causing these dB by dTs. And here, this is the large scale pattern that I'm showing. If you're going to have sudden variations in the field line currents, those are going to tend to occur on relatively small spatial scales. So there must be something within this pattern here that is producing variations in the currents and producing those magnetic perturbations on the ground. So some of the causes of these, the main mechanisms I'm going to be talking about are substorm onsets. These are where currents flow into and out of the ionosphere in the pre-midnight sector. We've got omega bands, which are a phenomenon that's observed in the dawn sector. And there's also, I'll talk very briefly about the Kelvin Helmholtz instability, which is due to surface waves on the magnetopores, which then feed along magnetic field lines down into the ionosphere. In common with most other workers, we're going to be using the SuperMAG network to look at these. You can see there's a very broad global distribution of these magnetometers. Unfortunately, there are pesky oceans all over the place, which kind of limit the availability of magnetometers in certain places on the Earth, but otherwise it's a pretty good network here. Most of the SuperMAG data is at 1 minute cadence. So what we tend to do is we look for minute-on-minute variations in the magnetometer measurements. 1 second data is also available, and I'll talk about that later on, but it's only available from a subset of these stations. So if you want as global coverage as possible, you use the 1 minute data. Now, in the literature, dB by dt greater than 5 nanoteslas per second is quoted as the kind of effective or hazardous kind of variations that we're looking at here. So in minute data, we're looking at 300 nanotesla changes per minute. So as I mentioned, we tend to look at minute-on-minute changes, and in a lot of what I'm going to talk about from now on, I'm going to be looking at changes of 100 nanoteslas, 200 nanoteslas, 300 nanoteslas, or 400 nanoteslas from 1 minute to the next. And we have data available for a long period of time. Here I'm going to be looking at data from 1995 to 2020, which covers two solar cycles. Okay, so in these panels here on the left-hand side, I'm just showing the occurrence. These aren't mean deflections. These are the occurrence of deflections in the 3 different components: N, which is north-south; E, which is east-west; and Z, which is up-down. And in blue, that shows the occurrence of negative deflections, so that's southwards or westwards. And red is positive deflections. And I'm showing 3 different years here: 2008, 2016, and 2003, which are years of differing solar activity from low to high. And so the first thing to notice, especially if we're looking in the north-south component here, which is that produced by the electrojets that I was talking about earlier, we can see that there's a broad local time region where we have negative deflections associated with the westward electrojet, and there are positive deflections as well, but these are limited to to near the dusk sector, really. And so if you're familiar with looking at the AU and AL electrojet indices, then AL will be controlled by the region that you see in blue there, and AU will be controlled by the region in red. It's always been quite surprising to me how limited the local time sector with positive deflections actually is. The other thing to note is that the occurrence of these perturbations is very dependent on the solar activity. If we look on the right-hand side, now what I'm actually looking at is the occurrence of those dB by dTs, those changes of greater than 300 nanoteslas from 1 minute to the next. And now we see the two hotspots that I was talking about appearing much more clearly. In 2008, where there was relatively low activity, we only see what I'm going to call spikes, these dB by dTs, in the pre-midnight sector and at relatively high latitudes. But then as the activity increases, then we see that the occurrence of these spikes increases, and the range over the local time range over which they occur broadens considerably. But nonetheless, even in 2003, it was clear that there was these two particular hotspots, pre-midnight and dawn. So one thing that we were particularly interested in this study was the solar cycle dependence of the occurrence of these spikes. And that's what I'm showing in the middle graph here. So if you look at panel B, this is the year-on-year occurrence of these spikes. And then the colors indicate the local time sectors in which those spikes occurred. So in green here, that tells you that spikes were observed in the pre-midnight sector. Dark blue is in the dawn sector, and light blue is all other local time, so mainly around noon and what have you. And the bottom panel shows us the sunspot number. You can clearly see the two solar cycles here. First thing that we notice is that the main occurrence of spikes is not at solar maximum, which one might expect, but is actually in the descending phase of the solar cycle. That's one variation. The other is if you look in panel C, which shows the percentage of spikes that occur pre-midnight or at dawn, we can see that there's a great variation with the time of the solar cycle. So at solar minimum, all of the spikes observed are pretty much pre-midnight, so associated with substorms, whereas the rest of the time, there's about 50-50 chance of seeing them pre-midnight and seeing them at dawn. And as we'll discuss later on, the dawn ones are associated with omega bands. Okay, I'm highlighting 4 particular years here of different solar activity, and showing those on the right here in order of increasing sunspot number, just to look at the local time distribution of these spikes once again. So if we look at the top panel, we can see that these spikes really do almost exclusively occur in the pre-midnight sector, and they're all in the north-south, or predominantly in the north-south component. If we look at 2013, then now the majority of spikes are seen in the dawn sector, and these are mainly in the east-west component. And as we go further up in activity, you see almost half and half occurring pre-midnight and at dawn. And if you look carefully at 2003, you might be able to see that there's a third population just beginning to peak out between about 06 and 12 MLT as well. So we believe there are actually 3 different hotspots in here. I should note that there is a local time sector between about 0 and 3 local time when we see very little spikes, irrespective of the level of solar activity, and that's always been something of a puzzle, and I'll return to that a bit later on. Okay, what I'm doing here now is looking at the possible drivers of these different um, uh, hotspots, the sorts of solar wind that is giving rise to them. So if we look in the middle panels here, we've got MLT along the x-axis, and then for each of the 5 panels, I'm looking at the occurrence of spikes with from the top down, from solar wind speed, the magnitude of the BZ component of the IMF, a measure of the dayside reconnection rate, the AL index, and the SIM-H index. And there are actually contours on this plot. The contours are indicating the occurrence of spikes, and then what the colors are, where there are spikes, the color is indicating whether they are mainly in the north-south component or mainly in the east-west component. So you can see that there's a very clear demarcation between the substorms in the pre-midnight sector and omega bands which are occurring in the dawn sector. If we look at the top panel, we've got solar wind speed. The solar wind tends to blow between about 350 and 800 kilometers a second. And here we get spikes right across that range. So solar wind speed doesn't seem to play a huge role in determining the occurrence of these spikes. But if we look at the BZ component, the substorm population tends to occur for negative BZ, but maybe between 0 and -10 nanoteslas. But the omega band population now tends to occur for lower BZ, so you need a more intense southward IMF to drive the omega bands. That then is reflected in the dayside reconnection rate as well, where the substorms tend to occur for lower values of the dayside driving, whereas the omega bands, you need quite intense driving to get these to show up. And again, we can see that this is reflected in the AL index and to a certain extent in the SIM-H index. So there are different solar wind conditions that give rise to these 2 different populations. Okay, just very quickly here, I'm showing some examples from the 3 different local time sectors that I've spoken about. Oh, I should say something very quickly. I forgot to say in the previous slide. If you look at the very right-hand side of these panels that I was just talking about, you might be able to see a population that I've labeled KHI for the Kelvin-Helmholtz instability here. The reason that we think that this population is Kelvin-Helmholtz instability is because it only appears for very high solar wind speeds around about 700 kilometers a second and higher. And if we look at the BZ component here, which I'm waggling my pointer here, they occur for around 0 BZ. You don't need dayside driving, particularly. You just need very fast solar wind for this population to appear. Okay, so here are 3 examples of the sorts of spikes that we get. On the left-hand side, these are examples of spikes associated with substorms. We've got 3 different SuperMAG stations here showing the north, east, and Z components. And the vertical lines indicate where dB by dt in excess of 400 nanoteslas per minute have occurred. And these are sharp southward deflections of the magnetic field, as you expect with substorm onsets. And these are occurring, if you look in the lower panels, these are occurring in the pre-midnight sector. They're occurring for low SIM-H. There is moderately southward IMF and pretty typical solar wind. If you look at the middle panel now, what I've labeled omega bands, the magnetic deflections have quite a different shape here. We see quasi-periodic variations in mainly the east-west component here, and these are occurring for more southward IMF, again, fairly typical solar wind speed and density. And these are all occurring in the dawn sector. So they have quite a different characteristics from the substorm spikes. And then finally, here is some on the right is examples of spikes observed around about 9 MLT. And you can see that these are associated with very rapid fluctuations in the magnetic field, very wave-like. So we think these are Kelvin-Helmholtz instability waves. And notice the solar wind speed is very, very high during this particular interval. Okay, so moving on slightly, I'm going to focus more now on these dawn spikes, because they're the ones that are least well understood. And I'm going to look at the context within which these dawn spikes appear. So this is a period of data which is about 3 days long, perhaps, roughly 3 days long. It's very complicated plot. I do apologize. The thing I want to kind of concentrate on is perhaps panel E here, which shows the AU and AL indices. And we can see a variety of different activity going on here, from very quiet activity to the characteristic signatures associated with substorms, where you have the negative deflection of the AL index. And I've highlighted some substorms occurring in the AL index there, which you can see. But I've also highlighted a period which I've named multiple intensifications, where we have rapid negative deflections in AL. They don't look at all like substorms, though received wisdom is if you see a negative deflection in AL, that is a substorm. But these look quite different. And so when I first started looking at these, I called them multiple intensifications, which is kind of code for I had no idea what was going on here. If you look at the two panels near the top, B and C, what I'm showing here are the field line currents measured by AMPERE, indicating that you've got the typical region 1, region 2 current pattern during this interval. I'm showing a cut across the dawn-dusk meridian here. Notice that the currents are fairly intense. That means there's lots of convection going on, but also those currents are expanded down to low latitudes. So this period of multiple intensifications is occurring during a strongly driven and expanded polar cap kind of interval here. And then in the top panel, I'm going to show this sort of plot quite a bit from now on. This is showing the local time distribution of spikes observed by SuperMAG. So midnight is along the middle of this panel. Anything occurring below the dashed line there is occurring in the pre-midnight sector, and everything occurring above the dashed line is occurring in the dawn sector. So you can see two different sorts of activity. We can see spots occurring in the pre-midnight sector, which are associated with substorms in the AL index. But we've also got almost continuous activity during this period in the dawn sector, and this matches, very closely that period that I identified as multiple intensifications. So what we want to do is look at what's going on a bit more in detail during this particular interval. So I've just highlighted the central portion of that diagram now, and now I'm showing snapshots of the field line currents from AMPERE. And superimposed on those snapshots are little cyan circles which tell you where instances of dB by dt are occurring. And on the right hand side, we've got auroral observations taken from DMSP. We've got both proton and electron auroras in these images here. So right at the start of the interval, there's no dB by dt going on, and the auroras are relatively dim in that top row. But as time goes on, we can see in the third row down, it's a bit difficult to see because DMSP only sees a small portion of the auroras, but you can see that the auroral intensity has increased markedly here, and we're seeing dB by dt mainly occurring in the pre-midnight sector. And then as we go down, we begin to see more dB by dt in the dawn sector. And if you look very closely at the auroral images, maybe second row up, you can see lots of intense finger-like auroral structures in that dawn sector, and it's these that we believe are giving rise to the dB by dt. We think these are omega bands. They don't look very much like omega bands, but we think that's what they are, and I'll talk about these in a bit more detail. The trouble with DMSP, looking at the auroras, is that it has terrible temporal resolution, so we can't really see how these things are evolving. So to look at that in more detail, I've gone to some historical data here, using observations from the IMAGE mission, which took auroral images from space, but at 2-minute resolution, rather than more like the 45-minute resolution that you get with DMSP. Doesn't have as good spatial resolution or sensitivity as DMSP, but it does have that temporal resolution, so we can see how things are evolving with time. So in the top panels there, I'm showing some snapshots of the auroras, and just to confuse everybody, I've rotated these so that noon is towards the left, dawn is towards the top, and midnight is towards the right in each of these panels. And hopefully you can see near the top here, let me try and highlight that, near the top here, you can see some periodic structures in the auroras, and we think these are omega bands. The next set of images here does indicate a sequence of images 2 minutes apart, and again you can see periodic structures in the dawn sector, and if you stare at these really hard you can see that they're propagating eastwards with time. So I've drawn a red circle there. What I've done is I've taken the auroral intensity along the circumference of that red circle, and I've stretched it out in MLT, and so that's what we're seeing in the two lower panels there. This is the auroral intensity at 2 different latitudes, wrapped out in local time. So midnight is towards the middle where the dashed lines are, and then dawn is towards the top, and pre-midnight is below that dashed line. Some things stand out here. We've got a big enhancement of the auroras in the pre-midnight sector here, and if you look down here at the AU and AL indices, we do see the characteristic AL Bay associated with the substorm. So we're seeing the substorm auroras in the pre-midnight sector here, and there are other times here, at this time here and later at about 16 local time, we're seeing these substorm onsets, which again you can recognize in the AL index. But we've got lots of auroral activity going on in the dawn sector as well. And if we look at the panel C here, this is showing the occurrence of spikes in MLT as measured by SuperMAG. And we can see hotspots again in the pre-midnight sector associated with those substorm onsets, but near continuous activity in the dawn sector. And that dawn sector activity takes the form of periodic structures in the auroras, which are moving eastwards with time. So at the start of this interval, you can see these structures here, which drift pretty slowly towards noon. Later on in this interval, we see again periodic structures here, but they're now moving much more rapidly, and it's these rapidly moving ones that are giving us the dB by dt on the ground. So one picture is that these periodic structures are embedded within the convection return flow and drift eastwards with time, and if that convection is very strong, they drift very rapidly. On the other hand, if the convection is slow, then they drift slowly. And that is perhaps giving us a clue as to what you need to get large dB by dt, because if these things are associated with magnetic deflections as they propagate over you, even for the same amplitude, if they're moving more rapidly, then they're going to give you higher dB by dt. So this is what we think is giving us these signatures. Here in this panel on the left now, I'm just showing the magnetic signatures associated with these things as they drift over. And again, you can see they have this characteristic quasi-periodic variations in the magnetic field. Here's some historical observations again of magnetic perturbations associated with omega bands. The thing I want to highlight here is that on the right-hand side, the amplitude of the magnetic deflections is of the order of a few tens of nanoteslas at most, whereas in the examples that I've been talking about here, we've got many hundreds of nanoteslas amplitude. And a key question then is, why is the amplitude so much larger in some of these events than in others? Okay, now I want to move on and show some work that Rosie Hodnett has been doing within our group. She's been also looking at these kind of omega band signatures, but she's studying them using all-sky camera data and looking at the ionospheric profile observed by EISCAT as these omega bands propagate over. So this movie shows you some omega bands from a period that she's particularly interested in. So this shows the field line current data from the period that she's interested in. Let's highlight the time that she's studying here, and you can see that this is almost a carbon copy of the event that I showed previously. We've got very enhanced field line currents. They're expanded down to low latitudes. Again, this seems to be the sort of activity that you need for these events to pop up. We can see in here that there's nothing particularly interesting in the solar wind speed or density, but we've got pretty negative IMF-BZ, so that's what's driving strong convection during this period. And in the magnetometer data, AU and AL, again, you can see these multiple intensifications that I was talking about. Below that, you can see the locations of the spikes. And again, you've got substorm associated clumps of spikes, which Rosie has highlighted with green arrows, but also near continuous activity in the dawn sector. What I'd like to point out here is that the vertical grey lines are substorm onsets that have been identified in the Newell and Gerlov substorm list. What that list does, it looks for any negative excursion in AL and labels it as a substorm. So according to this list, there are lots of substorms occurring during this period, but in actual fact, we think there are only 4, and the rest of these false substorm onset identifications are due to these fluctuations in AL. Just very quickly, to give a bit more context, we can see the field line current patterns on the left, we can see the convection in the middle, and we can see some auroral observations on the right. And mainly what I'm doing here is highlighting the location of EISCAT, which is marked by the white star in each of these cases. And we can see that that star is basically sitting right at the boundary between the region 1 and region 2 currents in the dawn sector. And underneath, quite a lot of fine scale auroral structure as observed by DMSP. So what Rosie did was she looked at the ionospheric electron density profile as measured by EISCAT as these omega bands passed over. And so she identified on the whole 3 different types of profiles. Type 1, that's indicated there, is when EISCAT was underneath, one of the holes in the omega bands, and then as the omega band itself approached EISCAT, went overhead, and then retreated again, you basically got this variation from type 1, type 2, type 3, and type 4, and then back down to type 1 again as the omega band retreated. And so we can see marked variations in the electron density associated with these omega bands. And really interestingly, we've got a secondary peak occurring at about 100 kilometers altitude. So that's lower than we normally get in the auroras. On the left here, these are showing, again, vertical profiles as measured by EISCAT of the electron density in the UHF radar and in the VHF radar, showing the temporal variability in the profiles here. And below that, there's a keyogram of the all-sky camera data. And so you can see that there's a very good correspondence between the appearance of the auroras propagating overhead and enhancements in the EISCAT electron density. Also on the right now, we're showing that there are very large perturbations in the Y component as measured at Tromsø. We've got very large variations in dB by dt, which is shown in that second panel. These are approaching plus minus 15 nanoteslas per second, which is very strong perturbations. And then the third panel there shows the location of the field line currents upwards and downwards with respect to EISCAT. And we can see that these are moving polewards and equatorwards somewhat over EISCAT as time progresses. And the dB by dt spikes that we're seeing occur mainly when EISCAT is sitting right underneath that boundary between region 1 and region 2. And as that boundary moves away from EISCAT, then the dB by dt's decrease. And then finally at the bottom, showing the AL index here, and we can see some spikes in the AL index around about the same times that we're seeing the dB by dt's. And so again, here Rosie's plotted out the EISCAT, sorry, the magnetometer data, the X components, the Y component from a variety of different image magnetometers here. You can see the large scale deflections in here, but also what's really interesting on the X component, she's superimposed the AL index in blue. And hopefully you can see that there is an excellent agreement between the perturbations observed in the image magnetometers and AL here. And what this is indicating is that AL is actually picking up these variations in the westward electrojet, and it's those that are producing the multiple intensifications. So these multiple intensifications are associated with this dawn sector activity and are not associated with substorms at all. So you've got to really look out for those. When you see a negative deflection in AL, don't necessarily assume that it's a substorm. And then finally, what we've done here is we looked at the ionospheric conductance or conductivity rather associated with the variations in the electron density. And sure, the Peterson conductivity increases as the electron density of the ionosphere increases. What I'm trying to show here is that the Hall conductance goes up even more, and that's due to this additional peak in the electron density profile at about 100 kilometers altitude, which is being produced by very strong or very energetic precipitation. So the reason why we're getting these very large dB by dt spikes is because the Hall conductance is being elevated by this hard precipitation associated with the omega bands, and you can see that also in rheometer measurements. We can see spikes in the cosmic noise absorption here associated with the passage of the omega bands overhead. Where does this additional peak in the electron density come from? Where do these hard electrons come from? Well, it's known that the temperature of the plasma sheet increases during periods of strong convection. And so that's possibly what we're seeing here, which is why you need this very strong convection to get these omega bands with the very hard precipitation that is then giving rise to this dB by dt. Okay, so that's just a brief summary of Rosie's work. I just want to very briefly talk about another couple of pieces of work done by Amy Fleetham and Gemma Bauer. So here's what Amy was working on. I'll try and rattle through this quite quickly. Amy was specifically looking at the 1 second SuperMAG data, so presumably better for looking at dB by dt than the 1 minute data. Unfortunately, there are fewer stations available with 1 second data, so the coverage is a bit more patchy. But what Amy showed was that she looked at 5 different geomagnetic storms, which are indicated on the right here, and looked at the distribution of spikes during these storms and tried to work out what it was within each storm that was giving rise to spikes in different local time sectors. And one thing that she noticed was that every storm was quite different in the distribution of spikes that was seen. And in particular, case B here, we've got quite a large population of spikes in the noon sector, which we don't tend to see a lot of the time, but clearly when conditions are just right, we can get this spot. And in this case, this was associated with the initial phase of the storm when a shock in the solar wind impacted the dayside magnetosphere and clearly gave rise to these noon sector dB by dt. So here again, Amy was looking at the location of the spikes with respect to the field line current pattern. And as I kind of indicated early on, we would expect the spikes to occur where there are field line currents, because you need these field line currents to feed the horizontal currents flowing in the ionosphere. And so we would not expect dB by dt where there aren't currents. But during this storm where we had spikes at noon, you can see on the left there that at the time of the arrival of the solar wind shock, we got spikes quite a way away from where the field line currents were sitting. So these spikes weren't produced by ionospheric currents at all, but must have been produced by the magnetopause current itself. So that was quite an interesting finding. What this is showing is if you stare at these plots long enough, there are green circles on here which indicate the spikes, and there are upwards and downwards field line currents. If you look closely, you might notice a preponderance of spikes associated with the red currents, the upward currents, and fewer associated with the blue currents. So I've said that we should get spikes where there are field line currents, but now it seems that it's predominantly where there are upward field line currents where we're getting spikes. And this is being shown in a more statistical fashion on the right-hand side here, where with respect to local time, Amy has identified how many spikes are associated with upward field line currents or with downward field line currents or with no field line currents. And especially in the pre-midnight sector, we get that these spikes are almost exclusively associated with upward field line currents. In the dawn sector, you get more of a mixture, but there's still a predominance of spikes associated with upward currents. Why is this the case? Well, we know that upward currents are carried by downward precipitating electrons. These impact the atmosphere, produce ionization, increase that whole conductance that we were talking about, and they do so in a kind of splashy fashion. So it's quite possible that these are producing very rapid fluctuations in the ionospheric conductance, and it's that's contributing to the magnitude of the spikes that we're seeing. Okay, so the last piece of work that I want to talk about is work that was done by Gemma Bauer. Gemma was also looking at 1-second data. One of the main things that Gemma found was that the 1-second data sucks. There's lots and lots of noise in the 1-second data. The 1-minute data is quite clean, but there are all sorts of instrumental effects in the 1-second data. That means lots of noise spikes, as it were, and somehow you need to distinguish between the noise spikes and the real spikes that we're interested in. And so Gemma developed a fiendishly clever automated algorithm to filter out or to distinguish between bad spikes and good spikes. What she was also able to do was get the algorithm to distinguish between spikes that occurred as kind of genuine spikes or steps in the magnetometer data, what she called non-wave spikes, or those which were associated with more wave-like fluctuations. So those are wave spikes. And looking at the right-hand side here, she was then able to look at the local time distribution of non-wave and wave spikes, and sure enough, there's a predominance of the wave spikes at dawn and in the pre-noon sector, and more predominance of non-wave spikes in the pre-midnight sector where we get substorms. So this is the final topic here. Again, this is Gemma's work. And she was looking at what drives these periods of multiple intensifications that I've been talking about, and these periods of dawn spikes. And I'm not going to go into a great deal of detail here, but if you look in the bottom panels here, these are showing the SIM-H index in 4 different local time sectors. Noon, midnight, dawn, and dusk. And the dawn curves are shown in green here. And during the periods when we have dawn spikes, we see that the green SIM-H curve is less negative than in the other local time sectors. So clearly these spikes are occurring during periods of asymmetric ring current. And again, Gemma's just showing this in a more statistical fashion on the right-hand side, where we have dawn spikes. The fact that the black blob there is displaced to the right indicates that the ring current is asymmetric at these times. What does this mean? People have known that the ring current can be asymmetric for some time, especially during intense storms. There have been various theories about what can produce this. So in the top panel here, this paper is distinguishing between periods when we have the normal substorm current wedge and when they think that there was an additional current wedge in the dusk sector. That could give rise to an asymmetric ring current, but Shinotani pointed out that if you wanted to have the correct sense of asymmetry, there are 2 ways of getting it. One is a dawn sector wedge, or that there is almost an anti-wedge at dawn, and it is this anti-wedge, now called the dawn current wedge, that is now the popular interpretation of this data. So it appears that when we have, apologies, that's an ambulance going past. Hopefully nobody's too hurt. When we get these multiple intensifications and these dawn dB by dTs, it's associated with this asymmetric ring current associated with an anti-wedge. Why is this important? Well, there's been modeling work done recently looking at these sorts of activities, and they have indeed identified this dawn sector wedge can appear in their models and be associated with bursty bulk flows in the dawn sector. We normally expect bursty bulk flows in the pre-midnight sector where there are substorms, but it appears if the conditions are right and the ring current is asymmetric, then the reconnection in the tail can be pushed towards dawn, and we get these bursty bulk flows, which are then associated with the formation of these omega bands. So things seem to be hanging together now in terms of the observations and the modeling. Okay, that brings me to the end of the talk. I'll just leave the summary up here, and please let me know if you have any questions. Thank you.